This week's lab is the Diels Alder reaction. So the overall reaction is written here. We're taking cyclopentadiene and we're reacting it with maleic anhydride, and that's going to undergo the 4+2 cycloaddition to give the Diels Alder adduct. The only product that we're going to see is the endo product, and we'll talk about that when we get to the mechanism. So the procedure is a simple one. We're going to weigh out 0.200 grams of maleic anhydride, and we're going to put it in some reaction vessel. The lab procedure calls for test tubes. I'm not sure if we're doing these in test tubes or if we have round bottom flasks that we're going to conduct it in, but there's going to be some reaction vessel that we're going to put it in. We're going to dissolve that up in a milliliter of ethyl acetate, and then we're going to add a milliliter of hexane to it. So we should have a homogeneous solution at this point. Then we're going to add 0.20 milliliters or 8 to 10 drops of cyclopentadiene. Cyclopentadiene has been prepared for us. It comes as a dimer, and I'll talk about that in the mechanism step. But it comes as a dimer, and it's been cracked already. It's separated into cyclopentadiene, and that's what we're going to be using. We're going to mix and make observations. Touch the flask. Does it get hot? Does it get cold? I want you to make those observations. If it's endothermic, it'll get cold. If it's exothermic, it'll get hot. It'll release heat to the surroundings, and you will be part of the surroundings if you touch that flask. After we get to room temperature, maybe 10 to 15 minutes, the product should crystallize out. We may have to scratch it a little bit. We may have to add a little bit of hexanes to facilitate that, but we'll see. Everybody's reaction should be different. We're going to filter the solids, wash them with cold hexanes, and air dry them. You're going to get the weight of that material to determine the yield, and then we'll take the melting point to see if it fits in the range of the expected product. So the mechanism, as I said, the cyclopentadiene actually comes as a dimer, and the dimer looks like this. Give me 1 second. So the dimer actually comes as the adduct, and these bicyclo compounds, you'll get good at drawing this stuff the more of them you do. All right, so you can see this is a dimer. This is two cyclopentadienes that come together, and then if we heat this, what happens is the retro Diels Alder or the reverse Diels Alder reaction, and we wind up making 2 molecules of cyclopentadiene from this. So the way this happens, we're breaking bonds. So we break this bond to form the double bond here. This double bond goes over here, and this one ships over here. So we have a total of 6 electrons moving in this, and you can see we wind up making 2 cyclopentadienes when that happened. So with our cyclopentadiene and our maleic anhydride, we're going to get, again, that 4+2 cycloaddition. So let me just erase this and draw this in a better orientation for this. I'll draw it the way it's going to react. Oh, I forgot the oxygen there. So I'm just redrawing that 5-membered ring to show the double bonds lined up this way and kind of bent up the CH2. That's part of this. And what happens for this, the diene acts as a nucleophile, and it attacks the electron-deficient maleic anhydride. And again, we get 6 electrons moving when this happens, and we wind up with the Diels Alder adduct. And again, you'll get good at drawing these the more you practice. And what we wind up with is the endo product, and I'll talk about why in a second. So the endo product is where the hydrogens are up, and the maleic anhydride component of this is on the bottom. And this happens due to orbital overlap. I'm not sure how much you learned about the cycloaddition in your class, but this reacts as the highest occupied molecular orbital because it's the nucleophile. The highest occupied molecular orbital means it actually has electrons in it, and this is the lowest unoccupied molecular orbital, or the LUMO, that reacts. And the lowest unoccupied accepts electrons. So this is the nucleophile, and this is the electrophile. All these bonds are formed synchronously, so all the bonds are formed at the exact same time. And let's see if I can draw this orbital overlap for you. So what happens here with the cyclopentadiene? I'm going to actually draw it as orbitals. All these p orbitals are listed like this, and the 5-membered ring of the anhydride kind of looks something like this, and I'll draw the p orbitals there, but there's also these p orbitals over here from the double bonds of the C double bond oxygen. And these orbitals of the carbonyl interact with the orbitals of the diene as well, forming this secondary, it's called secondary orbital overlap. And that's a stronger attraction for it. That's why they approach this way, and that's why we get only the endo product. I'll draw the exo product to show you the opposite. All right, so this is what the exo product would look like, where the hydrogens are on the bottom side, and this is up. So this is the exo, and we don't see any of the exo product in this one. It's exclusively for the endo, and it's because of this secondary orbital overlap that we get. All right, so this is more than enough information for you to draw out your mechanism. Again, when you do draw these structures, you want to use the template in ChemDraw. The template's that little rubber stamp looking icon that's on the side, and that'll open up a drop-down menu. Once that rubber stamp icon is there, you want to look for bicyclo compounds. Right. So once you click on the bicyclo tab, you should see things that look like this, and you can complete your drawing. All right, looking forward to it. Hopefully the snow holds out and we actually have class. I'll see you all tomorrow.